Hello, everyone. My name is David Stewart. I'm taking over from the lovely Aaron for the second half of this course. I hope I can keep up the high quality that he has no doubt set. I thought it might be a good idea, because we're doing so much, there's so many new concepts that we're coming across at the moment. So thinking about directional derivatives, vector fields, and one forms, and so on. But I try and give a bit more motivation for what you've seen already, so it sets us up in a good place for where we're going to go. So I think here's a good way to start thinking about these concepts, and it's just to imagine you've got a river. So if I draw something that looks like it could be a section of a river, then one thing that you might want to do, rivers are very good for this, is to work out the flow of the river at any given point, and then have a picture of how it moves, how the flow is changing as you move across the river. Well, it turns out that if you're in a bend of a river, the flow that you get is slower on the inside and faster on the outside of the bend. So you can imagine that maybe the water is moving a little bit there, but it's moving quite a lot here. And then obviously in the middle, we're going to get something in the middle. And if you continue doing this all the way around, you get a series of vectors at all the points in the river. You could even imagine measuring this. If you've got a sort of an object a bit like this, and I'll do a terrible job of describing this, but you could put a sort of spring in it with some sort of umbrella-y object at the end. You could put that inside the river at various points, and the speed of the flow is going to change the amount of force that's applied here. And so you'll get one thing that will happen is it will point in a certain direction. So that will give you a direction to your vector. It'll also be changing in terms of its magnitude. So you can really imagine actually going to a river, taking an object like this, and measuring at every point what these arrows should be. And what I'm going to tell you now is that you have precisely worked out what a vector field is. At any point, you get a vector. But it also makes some sense of the idea that if we've got a point here that's P and a point here that's Q, there's no particular reason to imagine that if you add P and Q together, that you could get anything relevant to the river. If this is our origin, then adding P and Q will take you somewhere over here, which isn't even in the river. So somehow we've given up on the idea of points being in the vector space, but we're keeping the idea of a vector space for the purposes of giving tangent vectors, as they be. And right, so this is an example of a vector field. What can you do with it? Well, you can integrate things over it. You can also apply it to various other quantities, for example, to create a directional derivative, where you can see that how a quantity is changing in the direction that's being specified by the vector and how fast it's changing. So if we just start by saying that the flow of the river gives you a vector field. And one thing we'll do in the courses as it progresses is to look at curves that you get. So you can imagine just allowing yourself to sort of, or putting a piece of paper in here and seeing how it flows across here. And, knowing the vector field will allow you to work that out, because it will say, at this particular point, I'm headed in this particular direction this fast. If I take a small amount of time, I'll know roughly where I am after that. So you could integrate that round, you'd actually work out exactly where you'll be at each point. So we can integrate this to get curves which go with the flow, going with the flow. So that's sort of an illustration of a vector field. What can we do with it when we're calculating directional derivatives? Well, we want a quantity that changes with the river. So you could think about maybe the depth of the river. So let f, y, be the depth of the river at point xy. Well, it might be a very interesting thing to know for various reasons how that the depth of the river is changing at every point in the direction of the flow. So calculating the directional derivative gives you a measure of how quickly the quantity, so in this case depth, is changing with the flow. So there might be some points in the river where the depth is staying roughly constant. There could be some points where it's getting a lot deeper, or whatever it is. And if you think about how you would work that out, well, you're going to want to know how is the depth changing with each partial, with each coordinate. So calculating the two. In this case, we've got two dimensions. So calculating the rate of change of the depth in each direction, and then saying, right, well, my flow is giving me a certain tangent vector, and if that's a big one, then I'm going quite a long way in that direction, and so my depth might be changing proportionally much. So it turns out that the right thing to do is just to take the scalar product, so the dot product, with the vector field at that point. So if my vector field is given by, let's say, given by f of x, y, e of x, call it g of x, y, e of x, plus h of x, y, e of y, then I'm just going to take the dot product of those things. And that's going to give me the directional derivative. So that's an interesting and useful thing to calculate. Okay, what about a one form? So a one form is a way to take a tangent vector, so like a vector given by a flow at a certain point, and produce a single quantity, a real number. And here's a useful one form that we might want to calculate. Let's say we want to know what the change in angle is relative to a certain origin. So if that's -0 and I've got a p I'm looking at the change of angle at P, I want to be able to take my tangent vector at P, apply this one form to it, and then it's going to give me a quantity that tells me how quickly that flow is changing. So to say that one form takes tangent vector, such as one given by flow, right? Flow of the river at a certain point, returns a real number which tells you something useful. And really the best thing to do is to give an example. So here is a nice one form. It's going to be the angle theta from the origin. And it turns out that you can write this down very explicitly. It's just the following. It turns out it's minus y over x squared plus y squared, the x plus x over x squared plus y squared y. So if I had the point 1, 1 here, I can work out what these numbers are. If I knew that P were something like, so this vector at P, the flow, is something like 1 minus 1. Then, so e.g. xy is 1, 1. And the vector field flow is vector 1 minus 1. Then you can plug all this stuff in. You put, so this is relative to the point that you're at, so you put these numbers in here. So theta is then going to be minus 1 over 2 dx, which is telling you you should just take the x component of the tangent vector that we've got, so that's 1, plus, and if I take 1 here, then I get 1 over 2, and then I take this dy tells me I take the component, second component of the flow, that's a minus 1 again. So at that point, I get a theta, which is a quantity that's telling me how quickly the angle is changing, and it's minus 1. It makes sense if you look at this picture. So this is moving counterclockwise the way I've drawn it. So the angle is going down. So that's why we get minus 1. So these are the sorts of ways I think are helpful to think about it. We're going to be looking at taking these forms, integrating them over curves. That will give us interesting information, like, for example, the change of angle. And in order to do that, we're going to need to parameterize some curves. That will be the content of the next